Okay, good morning, everybody. Thank you for joining us. I'm Paola Goria, and I'm the district manager for Regenesis in the Mediterranean district. Today, I'm joined by Alberto Cicognani, who's the remediation technical manager for A2A, and Christian Nielsen, who's the senior project manager at TAUW. And we will talk to you about a real site where we did in situ remediation for a diffuse chlorinated contamination. Before starting, I just have a couple of practical information. If you experience any sound or connectivity issue during the webinar, you can just close everything and relog in the webinar. Pay attention to close all the apps that can use internet, and if you have any additional issue and you cannot follow the webinar, don't worry, because you will receive in a few days an email with a link with the recording of the presentation, so you cannot miss it. If you have any question, please use the chat window you see on the right on your screen. You can type all your questions. We will try to answer to them at the end of the presentation, and if we cannot answer them directly, we will email you with the answer to your questions. After the presentation, you will receive an email with the certificate of presence, so everybody will receive it. And together with the certificate, there will be a short survey that we really ask you to fill, because it's very important to us. So I hope you enjoy it, and let's start. As I said, today we are 3 different people from 3 different companies, and we are going to discuss about a real site. So the site owner is A2A. So Alberto Cicognani is going to talk to you about the site introduction, the site background, the characterization activities, and the strategy about all the project. TAUW with Christian Nielsen will explain the consultancy part, so all the remediation plan, the treatment strategies, the goals, what we use to decide what kind of application to do. I will talk to you about the practical stuff, about the application, so my part will be more focused on what we did in the field. And again, at the end, TAUW will explain you the results and conclusion, and then we will start with the questions. So I leave the presentation to Alberto, and so we can proceed.
Thank you, Paola. Thank you for your presentation. I'll get into the topics of my presentation. I will talk to you about the site characterization and the site conceptual model. I'll give you some general background information. The current use of the site is industrial. The activities carried out at the site involve the management of municipal waste and some categories of industrial waste. As you can see in this picture, this is the area involved in the remediation. But unfortunately, on the same area, a new waste-to-energy plant is to be built. You can imagine that that is a challenging goal for the remediation design. The site contains several landfills and waste treatment plants. The total area of the site is 500,000 square meters, and the former use was agriculture. Here is another view of the area needing remediation. As I said before, this is the area where the new plant is scheduled. Let's focus on geological and hydrogeological setting. As you can see from the pictures, the predominant lithology is sand and silty sand. The ground water depth of the shell aquifer is 2 meters below the ground level, and the aquifer thickness is 9 meters. The hydraulic conductivity is 4.4 times 10 to the power of -4 meter per second, and the hydraulic gradient is 0.3. The groundwater direction is from northeast to southwest. How did we discover the contamination? During periodic groundwater monitoring, we detected 1,1 dCA in one monitoring well in a very low concentration, -1 microgram per liter. At the beginning, no other contaminants were found, and consider that no chlorinated solvents were treated at the site, either at plants or at landfills. So considering these assumptions, at the beginning, we suppose that 1,1 dCA came from a diffuse pollution in the shallow groundwater or from external source upgrading to the site. However, we carried out the investigation to understand if there is a source of contamination related to the site. The characterization process was carried out in phases. In the first phase, we installed new monitoring wells and we performed boreholes to identify the contamination plume and the source. We were able to find higher concentration of 1,1 dCA, together some traces of TCM and 1,2 dCA, but we are not able to identify the source. So we decided to shift to MIP technology. We did an investigation with a regular grid, 30 by 30 meters. We started from the monitoring well with higher concentration of chlorinated solvents and go up gradient. We did 50 MIP points that correspond to 700 meters of total vertical length. Finally, we identify the source in the saturated soil, corresponded to a terminal branch of a canal covered in the 80s before the A2A management of the site. Here is in the first picture the 3D model of the source by XSD sensor. You can see the source under that loop. And in the second picture, you can see the grid we performed for the investigation by MIP. In the source, we carried out geophysical survey, and we identified buried waste in an area very close to landfills. The waste are attributable to previous activity at the site before A2A management. Since the source and the contamination was down gradient of the landfills, we did activities to exclude that landfills and the leachate could be the cause of the contamination. I mentioned tritium tracer assessment to exclude this cause. After MIP, we perform new monitoring wells to describe the shape of the plume from the source to the boundary of the site, far about 300 meters from the source. The contaminants of concern are 1,1 dCA, TCM, and 1,2 dCA. The maximum concentration value at the source are for 1,1 dCE, 6,000 microgram per liter, for TCM, 15,000 microgram per liter, and for 1,2 dCA, 1,000 microgram per liter. The concentration values at the site boundary in the beginning are for 1,1 dCE is 40 microgram per liter, for TCM is 1 microgram per liter, and for 1,2 DCA is 10 microgram per liter. Here you can see some isoconcentration maps of the contaminants. As you can see, 1,1 DCE is the most widespread contaminant at the site. In contrast, TCM and 1,2 DCA are located mostly at the source. We carried out safety measures. We installed a large diameter well at the source to prevent the migration of the contamination along the groundwater flow. As you can see in this picture, we have a quick decreasing in the contamination, and then we had a stabilization. At the site boundary, we built an hydraulic barrier based on a hydrological model, and treatment plant for the extracted water too. We removed the buried wastes and at the source, and they were treated off-site. We also performed an health environmental risk assessment according to the Italian legislation. After this, we began to think about the remediation design. First of all, we conducted a pilot test to evaluate the remediation technology proposed by TAUW and Regenesis, Plustomp, and plus HRC. The pilot test, the run of the pilot test was positive, so we assigned the project to TAUW with the following goals. In the short term, remediate the site, minimizing the interference between the construction of the new plant, and reduce and maintain the contamination below the risk threshold values of the risk assessment. In the long term, allow the shutdown of the hydraulic barrier at the south boundary. Here are some lessons learned. How to perform a complex investigation on a wide area without info on potential sources. We proved the effectiveness of MIP technology for identifying the source area. We proved the effectiveness of geophysical survey for identifying buried wastes. And the pilot test run was positive, and we proved the effectiveness of the Plustomp and HRC for the plume and the source treatment. And we we learned how to minimize the interference between the construction plant and the design of the remediation. Actually, this is the argument of the next presentation by TAUW. So I now hand over to the next speaker, Christian Nielsen from TAUW.
Okay, thank you, Alberto. Good morning to all. I'm Christian Nielsen. I work in TAUW, as an European environmental consultancy company. And for this case study, we have elaborated the remediation design, and we coordinated the remediation execution activities. So I would like to share with you what are the most important elements that guided the design for the groundwater remediation. First of all, the area to be remediated is quite large, so we are talking about 2 hectares of impacted groundwater. And there's even if there is no huge concentrations regarding contaminants, but we have a very stringent threshold limits as remediation targets. So there's obviously one of the aspects that guided our remediation strategy. Regarding contaminants, as mentioned by Alberto, we are not talking about the most common chlorinated 18s, but we have the presence of chloromethanes such as chloroform, chloroethanes, and chloroethanes, as in particular 1.1 DCE. That is the presence is very interest the most part of the plum. Another important aspect is related to the time frame for the application. So we have a very challenging time for the execution of the remediation. That's why, because we have we have to consider that a new waste to energy plant is going to build, so it's something that we have to take in account, that we have let me say one shot for remediation. So most of the portion of the site will not be available anymore once the building of the waste to energy plant will be built. So it's something that we have to take in account for the remediation strategy, of course. And plus we have to, in a certain way, coordinate and overlapping the groundwater remediation also with the soil remediation. So we have to combine the remediation regarding soil in a particular part or portion of the site. And we have to coordinate all the activities with respect also to the groundwater remediation. So coming back to the treatment goals, we have, as I said before, we have very stringent remediation goals, as you see in regarding, for example, 1.1 DCE. The remediation goals are 0.05 microgram per liter, so it's something that's very challenging for remediation, of course. And also the other compounds that are present in the groundwater, we, as you see in a slide, we have to achieve a very important, very challenging remediation targets. So another goals, if we can say that, is regarding that we have to go forward with the remediation and maintain the pump and treat. So we have to, in a certain way, to understand the possible interference between pump and treat and injections that are the selected techniques for the remediation, as we see after. So summarizing the issues that are that guided our design, we need to be quick. We have to minimize the interference to the waste to energy construction activities, and obviously we have to attain high efficiency with very low concentration and extremely stringent targets. So it's something that we have to take into account for the remediation strategy. That means that we have one shot for the remediation. So we selected the in situ injections with a specific product engineered by Regenesis. And we need obviously to respect what are the all this project has to be a long-lasting region. So it's something that we have to inject something that maintain there's its efficiency for a long time. So we select a combination of technologies that includes enhanced reductive dechlorination through a biodegradation process, in situ chemical reduction, and in situ sorption and biodegradation. As I said before, we have to combine also the groundwater remediation with the soil remediation. So the soil remediation as represented in this figure, is this is the layout of the soil remediation activities, and in the right part of the slide, you can see the area that has to be where the soil has to be removed. We're talking in total about 20,000 cubic meters of soil that has to be removed. So it's something that has to be managed for a long time. We started the activities in the second quarter of 2023, and we completed all the excavation and the soil removal in 1 year after, so in March 2024. So this is obviously something that we have to take into account also for the groundwater remediation, and you see in the picture the interference with the groundwater remediation areas. So obviously this is something that we had to take into account for the coordination of all the activities. So in this slide we represented the scheme of the remediation approach. So this is a drawing of the plum. In the we have a pump and treat system in the downstream border of the sites, and in the opposite part of the plum, we have the higher concentration. So we have the source area where grid injection techniques is designed. So it's something that the approach is to try to remediate the higher concentration with a grid injection approach, and then the rest part of the plum with a permeable reactive barrier for complete remediation, and in order to assure the achievement of the remediation goals. So going details. So in this more or less what is the location of the grid injection in the right side of the figure. Then we have the two barrier. So in that case, we have also different approach for techniques. So in the source area, we think about in situ chemical reduction by using zero valent iron. So we go in details after for the explanation of the products, and we use also electrode donor that can implement also the biodegradation process. So we have a combination of chemical reduction and biodegradation process. And then we have the two permeable barrier that are composed by two line of injections. So the first one is related to again electrode donor, and the second one is thought about the injection of activated carbon-based products that is called plum stop. That's in order to combine the biodegradation and the sorption of the contaminants from and the removal from the groundwater. The same approach is in the downgradient barrier, so it's something that we apply also in the downgrade gradient. Just to remind that we had to take into account that there is also a future construction of buildings for the waste to energy plant. So in the area in red more or less represents the area where the future building will be built, and so this is as you can see in the picture, we need again to to complete the remediation before obviously the buildings will be built. So this is another representation of the hazard concentration for regarding the 1.1 DC and the location of the different remediation actions that we thought for the completion of the groundwater remediation. So I will let the floor to Paola in order to go a little bit in details about the selected product engineered by Regenesis.
Thank you, Christian. I will go just a little bit in details about the three main products we used in this remediation. 3D microemulsion is a long-lasting electron donor that has a very strong self-distributing capacity, and S-micro-CVI is a chemical reductive reagent used for the abiotic degradation of chlorinated compounds. Plume stop is a colloidal activated carbon that we use in the barriers. But just to go a little bit in more details, can you just go on with the slide, Christian? Thank you. So 3D microemulsion is, as I said, an electron donor. So the scope of the use of this kind of product is to enhance the reductive declaration of chlorinated compounds in particular. This is an engineered molecule made of different parts. So in particular, we have a part that is lactic acid, then some polylactates and fatty acids. The scope of this engineered molecule is to have a very homogeneous and controlled hydrogen release a long time. The longevity of this kind of product is up to 5 years, and the main objective is to be able to have the release very controlled a long time since the beginning down to the final end of the longevity. The other main important aspect that helps 3D microemulsion is the fact that it can be very well distributed across the aquifers. We can go on with the other product. So the colloidal sulfidated ZVI called S-micro-ZVI. Why we use this kind of product here? We used it just in the source. Here in the slide, we see the usual picture about the different degradation pathways for the chloroethanes, so PC and TC in particular, and the fact that when we use a zero-valent iron reagent, we can have the abiotic degradation of the contaminants. In this case, we didn't have PC and TCE, but we had in the source zone other highly chlorinated compounds like chloroform, and the idea to use the chemical reductive reagents in the source was mainly related to the fact that even if the concentration after the pump and treat system activity was lower than the beginning, probably hidden mass was present in the area. So we wanted to be sure to have something strong to treat with this kind of contaminants. Another important aspect why we use the colloidal sulfidated ZVI is the fact that sulfidation can increase the reactivity of the zero-valent iron with the reagents and make the ZVI not reactive with sulfates. Christian will show you after in this presentation that one of the problems in the source area was the high concentration of sulfates, and so the fact that we use a reagent that was not reactive with sulfate was a great advantage for us. The third product that we use is the Plume Stop. So it's a colloidal activated carbon product. You can see here in the video what does it mean to have a colloidal product, how it can be easily mixed with water. In the slide, you can see two pictures about granular activated carbon and powder activated carbon. So you can see the real difference between these two, this product with the other kind of activated carbon that can be injected. The main difference is the fact that it's very easy to be distributed across an aquifer. Why we use plume stop here, and why did we use barriers in this site where the concentration along the plume were very low? We used it just because the concentration were very low. So the scope was to be able to create some reactive barriers, some small volumes with the reagent, where we were able to capture the contaminants, so remove them fast from the dissolved phase and concentrate the contaminants in a small volume so that the degradation process could be enhanced. Because one of the main problems when you have a very low concentration plume to be treated is to find a way to have an effective treatment. If you want to just rely on biodegradation when the concentration is very low, it is very difficult to have an effective treatment, because the mass of the contaminant is very low and the activity of the microorganism can be not effective. Concentrating the mass in a small volume can help us in having a good degradation process. So now I leave again the presentation to Christian about the remediation plan.
Okay, thank you, Paola. Your explanations was very clear. So coming back to the design criteria, so we have we can focus on the source area criteria. So we have, as I said before, an irregular grid with in order to have an appropriate distribution of the products. We have obviously to take into account stoichiometric demand. We have to consider obviously the TOC, so the needed organic matter for a good fermentation. And we have to take into account, as mentioned by Paola, the sulfates. So we have some portion of the plum where we monitored a very high concentration of sulfates. So obviously this is can represent a competitor for as electron acceptors for the dechlorination process. So it's something that we have to take into account also for with respect to the dosage calculation. Regarding barriers, we have, as I said before, 2 injection lines, one related to electron donor and one related to the plum stop with the activated carbon based product. So this obviously we have to take into account again the for the dosage some site specific characteristics and in order to obtain the maximum effect from our remediation techniques. And we have to obviously consider the distance from the injection points by means of a pilot test in order to understand in a site-specific way what happened during the injection. So just to have an overview about the layout in the details of some details regarding the our remediation activities. This is the source area. So in total, we have we design 32 injection points with that are split in 2 different areas in the first areas with the purple points and the purple dots, we can see we have to take into account that there is a high sulfate concentration, so the dosage was calculated considering this competition regarding the electron receptors, and the dosage also varies also in relation to the depths, so in relation to also the soil texture, so the soil characteristics that differs a little bit from the shallow part and the deeper part of the aquifer. Regarding the last portion of the source area, we have a little bit lower sulfates, so the dosage obviously is calculated regarding a little bit competition, a little bit less competition regarding the reductive process. Regarding the layout of the barriers, so we have, as I said before, the two lines. The upgrading one is related to the electrode donor products with HRC, and the downgraded line is characterized by the injection of a plumb stop. The spacing between one point and another is 2 meters. We have 31 and 30 points, injection points for the two lines, and these are more or less the amounts of kilogram per point that has been designed. For the downgrade barrier, the assumption is absolutely the same. So 2 injection lines with a total of injection points of about 47 in total injection points for the two lines. So as I said before, we need a pilot test in order to verify the efficiency of our remediation actions. So we located the pilot test in this portion of the plumb. So in order to test in particular the plumb stop and the HRC injection efficiency. So we, as you see, the pilot test is not part of the injection lines designed by the full scale, but is a little bit in a downstream area, far from some meter far from the injection lines. That's why, because we during the monitoring of the groundwater, we have the periodical monitoring. We have seen that the higher concentration are a little bit in a different portion of the plumb with respect to the injection lines. That doesn't mean that the concentration has been disappeared in the full scale injection lines, but we need to have significant concentration in order to demonstrate the efficiency of our techniques. So this is the reason why we, in a certain way, move a little bit downstream the location of the pilot test. So in particular, we have this configuration for the pilot test. So again, we respect what are the approach for the barriers. So we have 2 lines of injection, one characterized by the injection of plumb stop, and the second one characterized by the injection of HRC. So this is the idea. So we have 2 lines with 7 injection points for the HRC and 8 injection points for the plumb stop, and we, in a certain way, try to apply the same approach that we are going to design for a full scale in order to understand this if this solution can be appropriate for our purpose. The pilot test, regarding the goals of the pilot test, we need to first of all understand and what are the distribution of the right distribution of the products during injections. So we use clean water in order to understand the optimal injection pressure and the optimal volume rate. We think about the method of the injection with respect to the tip that to be used. So we have two different kind of tip for ejection, and so we the pilot test gave us the opportunity to understand which was the right one. And also regarding the method of injection, so if button up, top down methodology for injection. So it's something that the pilot test gave us the opportunity to test all these options. And regarding during the injection activities, we understood that using the bottom up with the retractable tip from 12 to 3 meters, so in the deeper part of the aquifer, and top down with pressure activated tip from 2 to 3 meters below the ground level, we have seen that was the best solution for the injection. So that's why in order to avoid any possible daylighting event during the injections, and we in a certain way we have to modify and use these two kind of injection methods. Regarding the verification activities, so we collect some soil samples and some groundwater samples, and as you see, the plumb stop gave us the opportunity to see in a very evident colorimetric way what are the presence of what is the presence of plumb stop and distribution of the products in the injection area. So the black color is quite evident, both in the groundwater samples. Then, as you see, the soil carrots also in the directly in the soil. So this is a very easy way to understand the right distribution of the product. What are the results of the pilot test? Starting from the redox potential, we see that in the monitoring well that is placed just in a downstream position from our injection lines, we see that a very clear and evident reduction of the values, and with respect to the other monitoring wells. So it's something that it means that we created the right condition, the absolute condition for our remediation process. Regarding the contaminants in the pilot test, we have just 1.1 dca as contaminants that is present in the groundwater, but as you see in the graph, we have a very subtle reduction of the concentration just in the next monitoring campaign after the injection. So we see that we were able to achieve the remediation goals very quick and in a stable way. Stop. Another part of the pilot test regards the possible increasing of solubility of some metals such as iron, manganese, and arsenic. So as known, after the decreasing of the redox potential, it's possible that we can assist to increasing of some metals in the groundwater. And this is something that was also requested by the authorities in order to verify that our injection can in a certain way create some condition that can facilitate the solventization of these metals and so the increasing of the concentrations. That's why we collected some instant groundwater samples with respect to the distance from the injection lines, and we demonstrate that in a few meters the concentration in the groundwater completely disappeared. So we see that once we have the redox condition come back to the values that are naturally present in the groundwater, we can assist to the precipitation of these metals. So okay, I think it's that's all for a moment. I give the floor to Paola, maybe for give you a little bit some details regarding the execution of the activities.
Thank you, Christian. Now we talk about the practical part of the job. So I want to show you some slides related to the field activities. Here you can see that, as Christian already said, one of the main important things and one of the main challenges for this site was the stringent timing. So we had been requested to be able to make all the injection activities in 3 months, and this is what we did. So we started in the mid of April and finished in the mid of July. And in order to be able to do this, we used 3 or 2 rigs in parallel, depending on the moment. What you see here is just a screenshot of one of our programs. And the different colors are related to the different activities and the different rigs that we were using. So you can see here that we try to move the rigs across the site in different moments to be able to optimize all the activities. Here we can see how we move the rigs across the site. So we had a period where we had 2 rigs in the intermediate barrier and 1 rig in the down gradient barrier. Then we have the 3 rigs working contemporary in in the intermediate barrier. Then we have the 3rd rig moving again in the down gradient barrier for the final activities about the soil sampling. And at the end of the job, we had 2 rigs working in the source area. We had to work in the source area as the last part of our job because we had to coordinate our activities, as Christian said, together with the soil remediation. So this was also an effect of coordination. What did we do? Here you can see the plume stop that is mixed. As you can see, it's very black, it's very liquid, so it's in theory very easy to be injected, even if the injection volumes are pretty high. So one of the problems that we had to control and some of the challenges we had to afford was possible daylighting, also because the treatment was starting very shallow. Here you can see the drilling part. So the drilling was a direct push activity. In this case, we didn't have particular problems during the drilling. You can see here that it was pretty easy and pretty fast. It was less easy the injection part. So in some points we had to modify the injection rate, the injection pressure, change, maybe making some injection points split in two. So it was not very, very easy. Here we see in the mixing area. Here you can see the HRC preparation. So HRC is a product that is injected pure. So in this case, you don't see a mixer like we saw for the plume stopper, but it's just a small vessel with the piston pump. And this is used where when you need to inject a very thick product. So this is the preparation of the HRC for the injection. In these pictures, we can see the moment when we were working with the two rigs. For instance, this is the intermediate barrier. I want to evidence how close the two rigs were. And this means that it was very important for us, the coordination of all the activities, because we were injecting in points that were very close one to the other. So it was very important for us to be able to control very well all the injection activities. The same is for the source area. Here is the moment when we had the two rigs working contemporary in the source area, and again you can see that they were very close one to the other. This is an example of the software that we used during the injection activities. This software is called Open Ground, and this is very useful to be able to insert all your data online during the field activities and allow the office team to check all these data and control them in real time. So all our technicians had a laptop to use on the field, and they were used to insert all the information during the injection directly on this laptop, so that we were able from the office to receive this data in real time and check them. So here is, for instance, the starting of the input part for each point and each interval of injection. So each injection step, and we are talking about each 60 centimeters of each injection points, we were used to insert all the injection information. Here we can see that for each injection step, we could insert the flow rate, the pressure, the injection volume, timing, and also the notes. So if there was anything that was difficult or challenging or any problem, we were allowed to insert some technical notes to leave this information tracked for further evaluation. After this, the software allows to download the data as an Excel file. So this allowed us to be able to analyze and schedule the data, use them for the report or for statistics and all this other stuff. So that was very important for us compared to what is usually done in the field, so writing the data on the paper, because in this case we had a lot of injection points and different rigs working contemporary. So the fact that we were allowed to insert this data and control them almost in real time was very important. Another thing that we did to keep the job under control and keep the coordination with the technical supervisor, that was TAUW, was to have a continuous meeting. We were used to have a weekly meeting with the technical supervisor, and in these meetings, one of the things that we use was this kind of maps. So this is for the source, and then I will show you another one for the one of the barriers. But what is interesting is that we were used to have these maps with the indication for each injection points about the most important information. In particular, this was used to control the the progress of the activities. So for each point we had the date of completion. We had information about points where we had some problems. Here we see one in orange. That means that something was to be analyzed. Here we have another point that was in red. So we were able to discuss with the technical supervisor about what was happening. In this map, we can also see where we did and we sampled the groundwater to check the product distribution. So this was another way to keep all the activities always controlled and keep the possibility with the site technical supervisor to discuss anything that was happening on the soil. I talked about the sampling. As for the pilot, we did some verification testing activities for the full scale, in particular for the two barriers. So for the plume stop distribution, we took soil cores to check visually the distribution of the product. Here we can see a picture where the carbon is very easy to see. And we also took some instant groundwater samples in different points at different depth, again to check the presence of the carbon and the distribution of the carbon. In addition to this, we also had daily groundwater checking in the monitoring wells that were inside the treatment areas. So this was something we did to keep again the situation well controlled and to be able to understand the distribution of the product. Here we can see some of the challenges we had to afford. Daylighting was one of them. This is probably the worst point where we had the daylighting. I remember the permeability of the site is not very high. The groundwater is shallow. We injected a lot of reagents, so we had some daylighting problems, and we fixed them, changing the flow rate and the pressure of injection. We also had to work with the presence of subservices. Here you see a picture where we had to locate a point exactly in the middle of two pipes. We had a very bad weather. The job was done in 3 months, and for 2 of these 3 months we had very heavy rain. So we had to find a way to work anyway, because again the request for timing was very stringent. So here you can see the rigs working in a sort of pond. Here again it's the same problem, and we adapted our activities to be able to work anyway in this way. We also had some friends staying with us during the activities. And the last thing I want to show you about the field activities, how we managed the product. So we are talking about 3 different areas where we applied product. We had a lot of product arriving on the site. We had also a lot of empty drums to manage during the activities. So thanks to A2A that gave us a specific area where we stored our product and we were able to manage them. We also had to keep them very well controlled. So we had a stock tracker, and again this is something we did regularly. So every week or even more times per week, we were used to make a cross-control check to understand if the expected use quantities was correct, the expected presence of product left on the field was correct, the expected presence of empty drums was correct. This seems something that is very easy to do, but it's not. It's not also because we were working in different areas with different rigs, with different teams, and so it was very important to be able to have a supervisor and a general control about all this kind of stuff. And this is something that we did together again with our technical supervisor, that was TAUW. So I finished for the practical stuff and I leave the presentation to the results. I think we start being in a hurry, so I hope we can go a little bit faster for the results. I leave to Christian.
Thank you, Paula. So let's see the full-scale results. Starting from the redox potential. So in this slides, you can see the different results regarding the source area and the barriers. So as you can see, after the injection, we have a very quick decreasing of the redox values, and so that means obviously that the distribution of the products in a certain way cover all the monitoring valves in a good way, in an appropriate way. That's the same for the barriers. So we can see after the injection that the redox values drop down, and this is obviously the optimal condition for our remediation process. Regarding the contaminants, the results show in a very in general a good reduction after the injection activities. So in this case, we are in the source area, and the contaminant of interest is 1.1 dC. So we can see that the high concentration that we had before injection activities have been reduced in a very effective way after injection activities. In details, if we zoom up the concentration after the injection, we can see that the remediation goals are not yet achieved. So we have some residual concentration that is present in the groundwater, and we will see what happened in the next monitoring phase. Regarding the 1.2 dCA, also in this case, the remediation goals are not yet achieved, but in any case, we can see a reduction trend that is quite evident in the last period. So we are quite optimistic for the next phase of monitoring. So this is a zoom up of the most recent period. Regarding chloroform, in this case, if you can see in the source area, the chloroform, the starting concentration were quite significant. So we can appreciate a very immediate reduction of the concentration. And in this case, we completely achieved the remediation goal. So for the chloroform, the process was very, very effective. This is a zoom up of the most recent monitoring phase. And regarding the barrier, so in this case, the most important contaminant is 1.1 dC, and we see that in the intermediate barrier, the remediation goals have been achieved, and so we have a completely reduction of the concentration, as we've seen during the pilot test. We have completely achieved our target. The downgrade variant the same. So this is a very very linear trend of reduction of the concentrations, and in the last period we can see that we have also in this case achieved our remediation goals. I just have to remind you that for a 1.1 DCE, the remediation goals were very stringent. We are talking about 0.05 microgram per liter. So it's a very successful results for this part of the plan. So in conclusion, both barriers achieved in both barriers we achieved the remediation targets. So in all the monitoring wells, that's obviously the first successful results for our remediation actions. While in the source area, the monitoring is still ongoing, so we will see in the future if also in that part of that portion of the plume we will be able to achieve our concentration goals. We have in this case just to inform you that we have last year of monitoring, so we with respect to the remediation design, we have to conclude the monitoring at the end of 2026. Just to give you information, the waste to energy plant started in the construction started in the second quarter of 2025 and is ongoing, and the expected end is in the next 2 years. So I would like to underline the strong collaboration between all parties, and that has been very crucial to manage such a complex site and to achieve the results. So yeah, I think it was a very successful project, and I think we demonstrate the efficiencies of the remediation that we of the strategy of the remediation and the efficiency of the products that we use for the remediation process. Yeah, thank you.
Thank you, Christian.
The last slide.
Thank you so much. Yeah, I just want to thank you both again. Just an additional comment from me, in particular for our audience that is not from Italy. It could seem strange to you that we did this kind of remediation for contamination that was with so low concentrations. But I want to underline, as Christian already did, that the target for 1.1 DCE is 0.05 ppbs. So even if the starting concentration was low, because we are talking about just few ppbs, we had a decrease in concentration of more than 2 orders of magnitude. So, and as I said, and as also Christian said, the treatment of very, very low concentration is very often more difficult than treating higher concentration. So just to finish, we have a lot of questions. I read just a couple of them to our friends so we can answer to them. The first question is, when will you be able to switch off the pump and treat system? Christian, do you want to answer to this question?
Yeah, sure. That's the answer is in line with Italian legislation. So we can shut down the pump and treat system once we achieve the threshold limits set by the Italian legislation at the downstream border of the site. So we hope that we can in a certain way shut down very soon the system.
Okay, thank you. The second question I want to read is, why in the barriers there are 2 lines? Is it for having longer contact time? I can answer to this question. No, it's not really to have a longer contact time, but the main thing is that the 2 products that we used, so plume stop and HRC, cannot be mixed together. So HRC must be injected by itself. So we had to define an injection layout with different injection points, and based on the characteristics of the contaminants in the plume, in particular 1,1-DC, we decided to have the first treatment, so the first injection line with the donor, so to start having the degradation and keeping the activated carbon as the second part of the treatment. This was aimed to have a double stage treatment that was very important, again, for the scope of this site, that is to reach really, really low targets. So we are really running out of time. I thank you very much for following this presentation. I hope you like it, you enjoyed it, and I want to thank again Alberto Cicconiani from A2A and Christian Nielsen for TAUW for the help, both during all the activities and for being present today with us. Thank you again.
Thank you, Paola.
Stop.
Thank you. Bye.